All right, so here we have the definite integral as a limit of sums. So left and right sums are special cases of more general sums called Riemann sums. Now this is actually named after German mathematician George Riemann, who was back in the 1800s, 1826 to 1866, and they're used to approximate areas by means of rectangles. So if we let the f be a function defined on the interval, closed interval a to b, then we partition a to b into n subintervals of equal length. So delta x is b minus a divided by n. So same thing we've been kind of doing with endpoints a equal to x naught less than x1 less than x2 less than da 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 less than xn equals b. Then using summation notation, we have the following. For the left sum, we have, well, remember, we're going to start when we hit the left point of the curve. So we're going to have f x sub 0 times delta x plus f x1 delta x all the way up to x n minus 1 delta x. And so basically, we're going from 1 to n of the sum of f of x k sub x sub k minus 1 times delta x. So that would be for a left sum. Now for the right sum, we start at 1 because again, we're not going to start on the left side. We're going to start at the right side where it comes up and hits, and then we go that way. And so we start at x1 times delta x plus x2 when we plug it in, delta x, all the way up to xn delta x. And so this is from 1 to n again, but it's the f of x sub k times our delta x. Now, the Riemann sum says, well, S of n instead of R or L is going to be equal to f of C1 times delta x, C2 delta x, all the way up to Cn delta x. And again, we're going to go from 1 to n of f of Ck delta x. So in the Riemann sum, these CKs, each one of them is required to belong to the subinterval from k minus 1x up to the kth x. And left or right sums are the special cases of Riemann sums in which CK is the left endpoint or the right endpoint, depending on which one we're doing, either the x0 or the x1. Okay. Other type of Riemann sums exist where CK is chosen to be the location of the max or the minimum or the midpoint or some other number that's in that interval. So sometimes, how we had, let's say we had this one and we went and we're drawing crooked pictures, but we know we went from left or we went from right. Well, if we choose the middle, that one, what happens is it's going to underestimate a part of it and it's going to overestimate part of it. And so that kind of gives you more of an average of the two. And so sometimes the midpoint is the best one to use. And that's what they're meaning by the midpoint there. Okay. Now, if f of x is greater than 0, then each term of Riemann sum S sub n represents the area of a rectangle having a height f of ck and a width delta x. And we'll see that here on this slide on the next page. So here we have, x0, x1, x2, x3, x4. A is equal to this one. B is equal to this endpoint. And here we're doing C1, C2, C3, C4. Let's go back. And now if f of x has both positive and negative values, then some terms of Sn represent areas of rectangles and others represent the negatives of the areas of rectangles or the absolute values of it, depending on the sign of f sub ck. And again, that depends on if you're above the x-axis or you're below the x-axis. So sometimes when you're down here and you're below, your area is going to be negative, and so you want to just take the opposite of that or the absolute value, and then you can add them all together, and then area under this curve plus the area between here and here, we can get those areas. Okay, so that's kind of using these limit of sums to be able to find the areas. So what does that mean for this problem here? So it says consider the function f of x equals x squared minus 2x minus 10 on the interval from 2 to 8. Partition the interval into 3 subintervals of equal length. For each subinterval, let CK be the midpoint. Calculate this corresponding Riemann sum S3. All right, so first off, let's look what the graph looks like. So if we plug that in, we had x squared, and then we had minus 2x, and then we had minus 10, and we're going to go from 0 to 8, so we have to go a little further here, so let's go by 10. Let's go by a factor of 2. I'm not sure what the height is going to be, if it's going to be, yeah, it's not the right height here. So let's go from minus, I don't know, 20 up to maybe, I don't know, let's see if we have 864. Oh, we better do 100 because I don't know how big that needs to be. And let's see what we have here. All right, that's what we have. So, and we went by what are our units by two. All right, so 2, 4, 6, 8, 10. And so that's kind of what it looks like. It's below, so these are negative areas, and then when it gets above, these are going to be positive areas. Okay, so let's draw something like that on our graph here. So we're going to have, and again, it's just kind of a rough estimate. And so what was going to be, where does it cross over? That's going to be a kind of a key. We better find that out. That's going to be a little over 4 point something. So 4 is going to be about here. So 2's here, 6 is here, and 8's here. So 8 goes up to that point there. All right. Well, maybe. Anyway, so now what we're supposed to do is we're supposed to split it into equal intervals, 3 of them from 2 to 8. So here's 2, 4, 6, 8. So 1, 2, 3. So it looks like 2, something like that. So we have 1 interval, then we have 2 intervals, and then the third interval. All right, and so we're supposed to do 3 intervals equaling, find the subinterval, let CK be the midpoint. So the midpoint is going to be here. Maybe we should use a different color. That's going to be getting complicated otherwise. Let's erase that and change it to red. And so the midpoint will be here. This midpoint might be here, and that midpoint might be there or something like that anyway. So now, let's see, what else do we need to do? Now we need to kind of figure out what the points are. So now maybe we should change a color to draw our places. So our midpoint is here, so we can go left here, right here. Here we can go down and go to that. And then here it looks like we're gonna go up into that one. So we go down in that one, up in that one. And then here we'll go here and down, and then we'll go over. Okay, so this one kind of gets messed up because it's splitting in between two. Now this one just goes straight across. You know, if we went straight across here, that would kind of be weird. So we'll kind of do half and half on that one. So we'll have this area and we'll have this area here. So, all right, so now we need to figure out those points. And so the midpoint's going to be, and I've already figured this out to save a little bit of time. So that's 3, -7. And we have 5, 5, and we have 725. Okay, so those are those. So again, that's C1, C2, C3. And all of our calculations now. So what do we have? Well, for each subinterval, so we already knew how big a part it was because if you take 8 minus 2 divided by the number of intervals, that's going to be 6 over 3, so that's 2. So we knew it was going to be 2 apart, but we could also see that just looking at our picture. So sometimes you can see it in the picture, sometimes you can't. Now they want us to calculate the S3. S3 is going to be what? Well, that's going to be our delta x times f of C1, and then plus a delta x times f of C2, plus a delta x times f of C3. Well, what does that equal to? Well, our delta x is what? Well, that's going to be a 2. F of C1, well, that was -7 plus the 2 times f of C2, that was going to be 5, plus the 2 times, in this case, that was 25. So it's a -14 plus 10, so that's going to be what? -4, and then plus 50, so that's going to be 46. Okay, so that's what S of 3 is equal to. So that's our Riemann sum. So that's how we can use Riemann sums to calculate this as well. And again, we just used our midpoint in this case. All right, so let's stop there and come back for more.